Everybody's got the right to be happy. Don't stay mad, life's not as bad as it seems.
In this last video, I now want to talk about some things we can do with all of the stuff that we know about rational canonical form. So I'm going to talk about two questions that are discussed at this very end of section 12.2 of Dumb It and Foot. You'll be solving some very, very similar problems on homework 1. So the first question is, determine all similarity classes of matrices A with entries in Q that have characteristic polynomial x to the fourth minus 1 times x squared minus 1. So first, I just want to write this out in terms of its irreducible factors, x minus 1 squared times x plus 1 squared times x squared plus 1, which is irreducible over Q. All right, so I didn't say the size of this matrix, but remember, the characteristic polynomial of an n by n matrix is a monic polynomial of degree n. So this characteristic polynomial has degree 6. So A would have to be a 6 by 6 matrix with entries in Q. And what do we know? We know the minimal polynomial divides the characteristic polynomial. And because the characteristic polynomial has to divide some power of the minimal polynomial, every irreducible factor that occurs in the characteristic polynomial also has to occur in the minimal polynomial, not necessarily the same number of times, but at least once. So OK, now we can just write down the possibilities for the minimal polynomial. It must have a factor of x minus 1, a factor of x plus 1, and a factor of x squared plus 1. And that could be it. That could be the minimal polynomial. Or maybe it has two factors. The x minus 1 factor has multiplicity 2 times x plus 1, x squared plus 1. Or maybe that one has multiplicity 1 and the x plus 1 has multiplicity 2. Or maybe the minimal polynomial is the characteristic polynomial. We see that in this case, once we've chosen a minimal polynomial, we know the characteristic polynomial, that's uniquely going to determine the set of invariant factors. So why is that? Like in the first example, here's our minimal polynomial, our largest invariant factor. We know that the product of all the invariant factors is the characteristic polynomial. So the only thing missing is an x minus 1 and an x plus 1. So you can't have like x minus 1 is the first invariant factor and x plus 1 is the second invariant factor, and then the minimal polynomial is the third invariant factor, because the first invariant factor has to divide the next invariant factor. So the x minus 1 and the x plus 1 have to come together as the first invariant factor. So in this case, our set of invariant factors is x minus 1 times x plus 1, and then this minimal polynomial here. In the second case, the only thing missing between the ratio of the characteristic polynomial and the minimal polynomial here is just this 1x plus 1. So that has to be the first invariant factor. Similar for the next case. And in the last case, the characteristic polynomial is the minimal polynomial. So there is a unique invariant factor. OK, so what did we want to do? We wanted to determine all the similarity classes. And now we know all the possible sets of invariant factors. So given each one of these possible sets of invariant factors, there is a matrix in rational canonical form with those invariant factors. So let's just write it down. One matrix in rational canonical form for each of these four possibilities. What I mean, write out the corresponding direct sums of companion matrices of these invariant factors to give one representative for each similarity class. So I'm going to give an example, a different one than is given in Dumb It and Foot. If you take the first possibility, where you have two invariant factors, x minus 1 times x plus 1, x squared minus 1, and x minus 1 times x plus 1 times x squared plus 1 is the minimal polynomial, the case we're in this first row here, then a matrix in rational canonical form with those invariant factors is, if you take the companion matrix of x squared minus 1 in the first 2 by 2 matrix in the upper left corner on the diagonal, direct sum the companion matrix of x to the fourth minus 1, this 4 by 4 matrix on the next part of the diagonal. What are those companion matrices? Well, here the coefficients are -1 and 0. So we get a 0, 1, 1, 0. Remember, you get the negative of the coefficients. And here you get 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, and then 1, 0, 0, 0. This 6 by 6 matrix, where I didn't write in all the zeros here and all the zeros here, has invariant factors x squared minus 1 and x to the fourth minus 1. And any 6 by 6 matrix with those invariant factors is similar to this one. Okay, you write down a corresponding 6 by 6 matrix in each of these three cases as well. And that completely answers this question here. So this is a really common type of exam question. We could ask a similar question where you just change the characteristic polynomial a little bit to something else that's very close. Or instead, you could say determine all the similarity classes of matrices with entries in C that have this characteristic polynomial. What would be the difference? Well, the biggest difference is that x squared plus 1 is no longer irreducible now. That factors further as x plus I times x minus I. And you can think about how this process changes. And in the end, the answer is not that much. So I'm going to pause and erase and talk about a next problem from Dummett and Foote. Let's discuss our next problem. Determine all similarity classes of 3 by 3 matrices A with entries in Q satisfying A to the sixth equals the identity matrix. So what do we know? We have a 3 by 3 matrix A. The degree of the characteristic polynomial is 3. We know that the minimal polynomial has to divide the characteristic polynomial. So that tells us that the degree of the minimal polynomial is at most 3. We also know that A to the sixth minus the identity matrix is 0. So that means that the minimal polynomial divides x to the sixth minus 1. So how does that factor? I'll factor it for you. X minus 1 times x plus 1 times x squared minus x plus 1 times x squared plus x plus 1. These are two irreducible degree 2 polynomials over Q. All right, so what are we looking for? We're looking for a polynomial of degree at most 3 that divides this one. There are 9 possibilities here. So, and it has to have degree at least 1. Yeah, okay. I mean, you could have the 3 by 3 identity matrix, I guess. Okay, so you look at these possibilities and you got 9 possibilities for the minimal polynomial. So not all of them actually lead to a possible set of invariant factors. So you take your minimal polynomial and you ask, if this is my minimal polynomial, what are the possible sets of invariant factors I could have? You know, the minimal polynomial is the largest invariant factor, but what else could happen? So like what happens if you say, I want my minimal polynomial to be this irreducible polynomial of degree 2, x squared minus x plus 1, then because every invariant factor has to divide this irreducible degree 2 thing, and every minimum invariant factor has to have degree at least 1, the only thing of degree at least 1 that divides this is this quadratic polynomial itself. So if the minimal polynomial is x squared minus x plus 1, then every invariant factor has to be x squared minus x plus 1. But that's a problem because the sum of the degrees of the invariant factors, the product of all of the invariant factors, is the characteristic polynomial. So the sum of the degrees of the invariant factors is the degree of the characteristic polynomial, which is 3. But we can't take a product of a bunch of things of degree 2 and get something of degree 3. So it's just not possible for the minimal polynomial to be this irreducible polynomial of degree 2. Okay, so if you carry out this process, writing down all the possibilities for the minimal polynomial, seeing this one gives you a problem. Similarly, x squared plus x plus 1 would give you a problem. This leaves 8 possible sets of invariant factors. You can write out a representative for each of these similarity classes. You could write out the direct sum of companion matrices of these invariant factors. And what we're going to see, what we see is that x doesn't divide the minimal polynomial in any of these cases. All of these matrices are in GL3Q. They're all invertible. So what are we asking here you're saying that this is some matrix in GL3Q such that you take the 6th power and you get the identity. Okay, so clearly this matrix is invertible. And we know that the order divides 6. And what we're saying here is that we end up with these 8 similarity classes. Remember, in GL3Q, a similarity class is the same thing as a conjugacy class in GLNQ, right? Because what does it mean for two things to be similar? It means there's an invertible 3x3 matrix P, so that P inverse AP equals B. So two things are similar if and only if they're conjugate. So any matrix in GL3Q with order dividing 6 is in one of these 8 conjugacy classes. And if you look a little bit more carefully at the minimal polynomial, you can see that some of them actually, they have order dividing 6, but they also have order dividing 3, or they also have order dividing 2, that the order can actually be smaller than 6. But you can look more carefully and you can see which classes consist of matrices of which order. So you can write down all of the conjugacy classes consisting of matrices that have order exactly 6, for example. Okay, so you could ask, another direction you could go in is to ask the same question, but instead of having your entries be in Q, having them be in C. So how many similarity classes of 3x3 matrices A over C satisfy A to the 6th equals the identity matrix? And the difficulty here is that x to the 6 minus 1 factors further over C. So you get more possibilities. These quadratic polynomials that are irreducible in Q bracket x are not irreducible in C bracket x. So they factor further. So we can tackle this problem using rational canonical form, saying, okay, well, what are the possible minimal polynomials? What are the possible sets of invariant factors? But this one, it's actually a little bit easier to think about it in terms of Jordan canonical form, which is the subject of our next 2 lectures. And this is an example that Dummett and Foote come back to in section 12.3.